Hi everyone, and welcome back to the MCAT A series of lectures in physics. This final video will also be our second video on atomic and nuclear physics. In the previous video, we described that electrons can only exist in certain discrete orbits. We will extend on this idea by looking at the orbital structure of the simplest possible atom, namely a hydrogen atom. By only allowing the electron to exist in certain states, we have, in a sense, quantized the electron. I will then introduce various quantities associated with this quantization, for example, the principal quantum number n and the number of electrons per orbital. I have already discussed the ground state and excited states of electrons in an atom, and I will continue this discussion with an emphasis on the resulting absorption and emission spectra. I will then finish this video by discussing two principles related to quantum physics that you need to know for the MCAT. That is, the Pauli exclusion principle and Heisenberg's uncertainty principle. As I described in the last video, the electrons which surround the nucleus in an atom are only found in certain discrete energy shells. I also emphasized that due to this quantization, only light waves of specific frequencies and energies can be absorbed and emitted. This is because, in order for an electron to move from one energy level into another energy level, it has to either absorb or emit an exact amount of energy. Let us look at this in more detail for the simple case of having just one proton and one electron, in other words, a hydrogen atom. For this atom, we of course have the proton in the center in the nucleus, and I have drawn the first few of the possible orbits that one electron can be placed in. Each shell corresponds to a particular what we call principal quantum number n. That is, the first shell is known as n is equal to 1, the shell that is slightly further out is n is equal to 2, and so on. Remember also, as I just stated, only light with particular frequencies and energy can be absorbed and emitted. As different frequencies correspond to different colors, we can then consider the spectrum of hydrogen. That is, the color of the light waves that are absorbed or emitted when an electron jumps from one energy level to another. I encourage you to look up online what the hydrogen absorption and emission spectra look like. Finally, I also stated that because the position of the electron is quantized, the resulting energy of the electron is also quantized. For the simple case of a hydrogen atom, there is in fact a simple relationship between which shell the electron is in and its resulting energy. The energy of an electron in its nth shell, E sub n, is simply equal to minus 13.6 electron volts divided by n squared. The minus sign here indicates that the electron is in a way bound to the atom. That is, if that electron is to move further away from the atom, positive plus energy has to be added to the atom. This formula can also be used to calculate the energy associated with the light waves that are absorbed or emitted. For example, if we want that one electron to jump from the n is equal to 1 state into the n is equal to 3 state, the energy of the light wave that has to be absorbed will be equal to 13.6 over 3 squared minus 13.6 over 1 squared. We can also use the same equation in the opposite sense and work out the energy of the light wave that is emitted if the electron instead jumps down from a high energy level to a low energy level. Up to this point, we of course have been assuming the Bohr model of the atom. One assumption in this model is that the atom is one-dimensional. Therefore, as we see in this diagram, we only need one quantum number n to completely define what a shell is. However, of course, in general, an atom exists in the 3 dimensions. Because of this, not only do we have to worry about the size of the shell, but also its shape and orientation. Because of these two extra factors, we also need 2 more quantum numbers to fully describe the atom. More generally, we are now going to talk about orbitals. Orbitals that have the same size, in other words have the same value of n, form a shell. However, within this shell, these orbitals have different shapes and orientations. The first of the three quantum numbers we of course already have described, this principal quantum number n, and it defines the size of the orbital. As this quantum number n increases, the size of the orbital increases, as we can see in this simple case of the hydrogen atom. The next quantum number, known as the angular quantum number L, instead describes the shape of the orbital. It turns out that the orbital can have many different shapes. For example, L equals 0 corresponds to the simple shape of a sphere. L equal to 1 instead corresponds to a polar shape. L equals 2 corresponds to something that looks like a clover leaf, and it gets more complicated from there. I encourage you to look at different shapes of orbitals in your own time. Of course, a sphere looks the same no matter where we are looking at it. However, for shapes defined by angular quantum numbers greater than L is equal to 0, the orientation of that orbital does matter. Thus, we need a third quantum number known as the magnetic quantum number m. The reason it is called the magnetic quantum number is outside the scope of the MCAT, but it is because the effect of different orientations was first observed in a magnetic field. You may already know what I'm about to tell you about electron configurations, but I will recap it here just to be sure. There are in fact rules governing the allowed combinations of these three quantum numbers. Firstly, as we saw already with the principal quantum number n, all three quantum numbers are always integers. They are never fractions or decimals. This is of course the basis of quantization. Also, as we already know, the principal quantum number cannot be 0. For example, as I have here, the first shell is n is equal to 1. The angular quantum number L is any integer between 0 and n minus 1. Therefore, for example, if n is equal to 4, L can be any value of 0, 1, 2, or 3. Finally, the magnetic quantum number m is any integer between L and minus L. Therefore, if L is, for example, 3, m can be minus 3, minus 2, minus 1, 0, 1, 2, or 3. In order to describe what orbital we are talking about, chemists and physicists typically use the notation I'm going to present you. As I already described, orbitals that have the same principal quantum number n form a shell. Also, orbitals within a shell are divided into subshells that have the same angular quantum number L. The shell and subshell in which an orbital belongs is usually described by a number followed by a letter, for example 2p. The number represents the quantum number n, that is for 2p n is equal to 2, and the letter identifies the subshell, that is the angular quantum number L. Of course, what do I mean by a letter? I have said that the angular quantum number is of course a number. Well, it turns out, and it's mainly because of historical reasons, we represent different angular quantum numbers by letters. L equal to 0 is represented by S, L equal to 1 is represented by P, L equal to 2 is represented by D, L equal to 3 is represented by F, and after that it just goes alphabetically. L is equal to 4 is represented by G, L is equal to 5 is represented by H, and so on. Because of these rules, there are only certain electron configurations that are allowed. These configurations are, as I've shown here, and as you can see, they take the form of a triangle. I leave it to you in your own time to consider why, using the rules I presented in the last slide, that, for example, the 2D shell is not allowed. I would now like to turn our attention to the first of the two principles in quantum physics you need to know for the MCAT. While its description and understanding is outside the scope of the MCAT, it turns out that all quantum particles have wave-like properties associated with them. For example, even the position of a quantum particle can be considered wave-like. As it is wave-like, it means that its position is in a sense spread out. If we apply this fact to certain quantum equations, an interesting result pops out. This result is known as the Heisenberg uncertainty principle, and it tells us that it is not possible to measure the position and momentum of a particle simultaneously with exact precision. Instead, there is some uncertainty related to the position delta x and uncertainty related to the momentum delta p. The uncertainty principle tells us that this uncertainty in the position multiplied by the uncertainty in the momentum is always greater or equal to what is known as h bar divided by 2. H bar is known as the reduced Planck's constant and is simply equal to Planck's constant divided by 2 pi. The reason why this is introduced is because it turns out in quantum physics, h bar turns up a lot, and therefore to save ourselves writing h over 2 pi all the time, we instead write h bar. More importantly, however, is what this principle is actually telling us. It says that there is no way that we can exactly know both the position and momentum of a particle at the same time. If we know its momentum exactly, there is no way that we can know exactly the particle's position, and vice versa. A common misinterpretation of this principle is that many students and scientists alike believe that this principle is due to the fact that in order to make a measurement, we must disturb the particle in some way. As a simple example, if we wanted to measure the position of a particle, we could consider shining light on that particle and measure how long it takes for that light to be reflected back into a detector. However, by shining light on that, we are of course hitting that particle with light, thereby causing that particle to somewhat move. Thus, many students mistakenly believe that the uncertainty principle arises from disturbances caused by making measurements. However, as I've just stated, this is not in fact the case. The uncertainty principle arises from the fact that quantum particles are inherently wave-like. We can only know the position and momentum of a particle with a certain probability. The final subtopic in this topic, and indeed on the course, is known as the Pauli exclusion principle. This principle simply states that no two electrons in an atom can have identical quantum numbers. This principle, in a sense, is what determines the shape of the periodic table. There is in fact a fourth quantum number called the spin of a particle that is outside the scope of the MCAT, but when considering all four quantum numbers together, it turns out that, due to the Pauli exclusion principle, only 2 electrons can exist in the first shell, 8 in the second shell, 18 in the third shell, and so on. There is a limit to the number of electrons that can be in a particular shell due to the Pauli exclusion principle. This then wraps up our discussion on atomic physics and nuclear physics. As this was a short video, let us now finish the topic by considering 2 questions that are of similar style to the MCAT. This first question is testing our knowledge on shells, subshells, and orbitals. The question asks us, what is the number of electrons that the nth shell can hold? Is it 2, n over 2, n squared, or 2n squared? In order to work this out, let us break it up into 2 different parts. Let us first calculate the number of orbits per shell, then calculate the number of electrons per orbit, then multiply these 2 numbers together to get the number of electrons per shell. To determine the number of orbitals per shell, let us look back at our rules for electron configuration. First, we know that the magnetic quantum number m can be any integer between -L and +L. This means that there are a total of 2L plus 1 possibilities for the quantum number m. -L to -1, 0, and 1 to L. If you add these together, you get 2L plus 1 possibilities. Of course, L can also be many different numbers. We have to sum up this 2L plus 1 over the range of possibilities of L. Remember, L, the angular quantum number, can be any integer between 0 and n-1. Thus, overall, the number of orbitals per shell is equal to 2L plus 1 summed up between 0 and n-1. If you are not comfortable working this out, don't worry. You just have to know what it is. But if you think you can work it out, I encourage you to try it. If you do it, you get that it is equal to n squared. Thus, the number of orbitals per shell is simply n squared. To work out the number of electrons per orbital, we need to use a fact about this fourth quantum number, which I only briefly described, namely spin. In the case of this spin number, there are in fact only two possibilities, what we call spin up and spin down. Because of this, there are in fact only 2 electrons per orbital. Thus we have n squared orbitals per shell and 2 electrons per orbital, therefore overall we have 2 electrons per shell. Thus the correct answer is option D. This result explains the electrons in the first few shells that you have perhaps seen before. For example, for the first shell, for n is equal to 1, there are only 2 electrons. This is because we have 2n squared, which is 2 multiplied by 1 squared, which is simply 2. For the next shell, the n is equal to 2 shell, we instead have 8 electrons, 2 multiplied by 2 squared. Next, in the third shell, we have 18 electrons because we have 2 multiplied by 3 squared, and so on. As our final question in this series, let us double check that we understand something that is fundamentally important in physics but often overlooked, namely units. In particular, this question is asking us what the units are of Planck's constant h. Is it kilograms meter per second, kilogram meter squared per second, kilogram meter per second squared, or kilogram squared meter squared per second? The way to approach such questions is, rather than memorizing units, the units can be quickly derived by considering equations that contain the variable. For example, we have seen Planck's constant h in the equation for the energy of a light wave. The energy of a light wave capital E is simply equal to Planck's constant h multiplied by the frequency of that wave f. Rearranging this for Planck's constant, we see that Planck's constant must have the units of energy per frequency, in other words, joule per hertz. Of course, this is not one of our 4 options. All our 4 options are in base units. We must convert joules per hertz into base units. While hertz is the easiest to do, remember a hertz is simply a per second, therefore 1 over hertz is simply 1 over a per second or a second. A joule per hertz is simply a joule second. What about a joule? Well, we can use any of the equations that we have for energy to determine what a joule is in base units. For example, here I'm going to use the kinetic energy equation, namely E is equal to a half mv squared, but you can also use other equations like the potential energy equation, and I encourage you to try that in your own time. Thus, we see from this equation that a joule must be equivalent to the units associated with mv squared, in other words, kilogram meter per second squared. Thus, a joule is equivalent to a kilogram meter squared per second squared. Hence, the units of Planck's constant are joule seconds, in other words, kilogram meter squared per second squared multiplied by a second. Simplifying this down, we finally get that the unit of Planck's constant is kilogram meter squared per second, and therefore the correct answer is option B. Let us now recap this final video on electronic structure and what was in part an introduction to quantum physics. I began by returning to the Bohr model of the atom, in particular looking at the simplest possible atom, namely a hydrogen atom. I introduced the principal quantum number n that defined each possible shell that one electron could exist in. When this electron jumps from one shell to another shell, it either absorbs or emits a light wave. Therefore, we can consider both the absorption and emission spectrum for hydrogen, and I encouraged you to look up online what these actually look like in your own time. I then moved away from the Bohr model and assumed that the atom was, as it is, three-dimensional in shape. By making this generalization, I had to introduce two more quantum numbers to take into account the fact that each orbital can have also a shape and orientation. Due to various rules regarding the relationship between these quantum numbers, I then gave examples of possible electron configurations that are allowed under these rules. I then finished this video by looking at two principles that are important in quantum physics. The first principle, known as Heisenberg's uncertainty principle, stated that due to the inherent wave-like nature of quantum particles, it is impossible to know the position and momentum of a quantum particle simultaneously. Instead, in the best case scenario, the uncertainty in the position multiplied by the uncertainty in the momentum is equal to h bar, which is h over 2 pi, divided by 2. In general, the product of these two uncertainties is greater than this value. Finally, I talked about what is known as the Pauli exclusion principle, which simply states that in an atom or molecule, no two electrons can have the same quantum numbers. As I just showed in the first of the two questions, this means that only two electrons can exist in each orbital. This also, in a sense, is what governs the shape of the periodic table. This now finishes our discussion on atomic and nuclear physics, and on the physics portion of the MCAT as a whole. I hope these videos will be useful to you in your studies, and I wish you the best of luck in your exams going forward, and in particular in the MCAT.